Log on, tune in, find out. Another good idea from Cambridge.
So, thanks very much. It is a pleasure to come back here. So, I met Eric Sommers here, and we were sharing the same office for a few days. And on the last day where we were together, we had some idea of something to do together. So, we didn't really collaborate here, but it was the starting point. Yes. And then it became a bigger and bigger project, and soon it became a project with 4 people, so Basse-Normandie, Paul Levy, Eric Sommers, and myself. So as Wolfgang pointed out, it's not so easy to collaborate in the distance. But yeah, if you saw a talk with the same title before the summer, I should say right away that we did some progress. Because we met in Beijing in July, at least 3 of us. So we are interested in singularities of nilpotent cones in exceptional types. So the singularities of nilpotent orbit closures are quite complicated. But the first problem we can look at, if we want to understand the kind of singularities that appear, is to look at generic singularities. So that's the problem you have in mind. But the general aim is to understand better the geometry of these nilpotent cones. So I said it becomes a bigger and bigger project, but so the first thing I said is to understand the generic singularities. So if you have a nilpotent orbit closure, you can remove the orbit you started with and look at the orbits that are open in the complement. And you want to understand the singularities along each such smaller orbit. So this we call the minimal degeneration singularities. And it's all up to smooth equivalence, so I will explain what it means. But so if you look at the poset of orbits with inclusion of closures, this is like looking at intervals of length 2. But if we can understand bigger intervals, then we are even happier. So we don't want to restrict to this. But okay, and in particular, there is very nice intervals related to some special orbits, which were introduced by Spaltenstein and Lustig. And the definition is not geometrical, but there are some very interesting geometric properties. And there is a conjecture by Lustig about these special pieces that we are interested in. And there is also this Lustig-Spaltenstein duality. So if you look at the nilpotent orbits in type A, they are parameterized by partitions, and you have an order reversing involution of those. In other types, it's not like that, but if you restrict to these special orbits, then you have an order reversing involution. And you get the same poset of special orbits for dual types, long-length dual types. But actually, it's better to think of this involution as an order reversing bijection between dual nilpotent orbits of dual types. And so we have quite different backgrounds. So we are working on the same problem, but we may have different things on the back of our minds. Like, so I worked before on the modular Springer correspondence. So these singularities encode information about decomposition numbers of Wien groups. And so we compare singularities in different nilpotent cones. So this means, for example, that some decomposition numbers are equal. So Basse-Normandie is a genuine geometer. So he does like complex geometry. Is interested in the Mori program. And also Eric Sommers worked on the normality problem as well. And so it's all related to these things. So I said we are working up to smooth equivalence of singularities, so I will give a precise definition. So we have 2 varieties, x and y, with 2 marked points. And we say that they have the singularities are smoothly equivalent if we can find another variety Z with two morphisms and a point Z which maps to X and Y, and the morphisms should be smooth at Z. So it is an equivalence relation. So it may look a bit strange, but I will explain more. So first, if you have an algebraic group acting, which will be the case here, it only depends on the orbits of the point you are looking at. So it's convenient to write singularity of X along an orbit, O, so at any point in the orbit. And so this smooth equivalence, it doesn't preserve the codimension. So the idea is that if you have a product locally of something smooth by something singular, you are not interested in the smooth part. So if you take local rings and completions, then they are isomorphic up to tensoring with this ring of power series, formal power series. So which is formal functions on affine space. So it's really, it's the same kind of information as working in the analytic topology locally. And so what does it tell you, for example? If you know the local intersection homology of one singularity, it will be the same for the other one. The only thing is, so that's at a point, and if you are interested in the strata and the local systems, then you have to work more. So I will call N the nilpotent cone in a simple complex Lie algebra, so I work over the complex numbers. And we call G the adjoint group. So there are finitely many nilpotent orbits. They are ordered, as I said before. They are all even dimensional. And so, as I said before, we want to describe the generic singularities and possibly even deeper singularities. And so why do we work about exceptional types? Because this problem was solved for classical types by Kraft and Procesi in the 80s. And so only and by Kraft for Juteau as well. So we only need to work about the others. And as I said, we don't care about taking a product by a smooth thing. So there is no harm in taking a slice. So there are very nice slices for the nilpotent cones, the Juteau slices, which we have already seen. So if you have a nilpotent element, you can embed it in a SL2 triple. And then if you take this affine space, so E plus the centralizer of F, it's transverse to the orbit of E. And so you don't change the singularity type if you intersect with this line. So there is one singularity which is very well understood, is the singularity of the nilpotent cone along the subregular orbit, which is a unique orbit which is open in the complement of the regular orbit in the nilpotent cone. So it is of codimension 2. And if you take a transverse slice, you get an isolated surface singularity. And if you start with ADE type, you get a simple singularity of the same time. So this is a Briscoe theorem of 1970. And besides, you can use Gauss-Stenig simultaneous resolution to get a Versal deformation of this. So what about the other types? So Slodoway explains that. You have, the simple singularities are classified as they are only ADE classification. So as all is often the case, for non-simply case, you have to unfold the diagram in some way. And so actually, you have a singularity of ADE type, but with an action of a finite group, which is if you have started from adjoint type, so it's a group of components of an element in the subregular element. And so we want to keep track of these symmetries. So we will call, for example, A2n minus 1 with S2 action We'll call it A2-1 plus to remember that there is this S2 action. And also we will even call it Bn. So it's like the subregular in Bn, not forgetting the action. And the only case when we can have S3 is for D4, which gives the G2 case. So that's the top of the Hasse diagram of the nilpotent orbit. And you can look at the other extreme. So down below, you have the trivial orbit, 0. And just above it, you have the minimal nilpotent orbit. So it's the orbit of a highest weight vector for the adjoint representation. So a long root. It's the orbit of long root elements. So for example, in the SLN case, it's the orbit of this element. So it's rank 1 nilpotent matrices. And in all types, it has a very nice description. If you look at the closure, you just add the trivial orbit. And there is a resolution obtained like this. So you have some G mod P, where P is a stabilizer of a highest weight line in the adjoint representation. You have some line bundle on this. And if you contract the null section, you get exactly the minimal orbit closure. And so the simple singularities, we denoted that by capital letters. And these minimal singularities, we denote them by lowercase letters. And so they are of codimension greater than 2, except A1, which is the same as the previous A1, because in SL2 there are only 2 orbits, so minimal on 0 is the same as regular and subregular. And they can also come with symmetries. So I will just say a few words of Kraft and Procesi's results. So for SLN, it's easy to explain. And so their motivation was a normality problem for nilpotent orbit closures. And so they describe minimal generations for classical types. And so for SLN, there is a row and column removal rule. So if you are looking at the singularity of a nilpotent orbit closure along a smaller one in SLN, both are indexed by partitions. And if you have the first row or the first column which is the same, you can suppress it, and you get the same singularity. So for representation series, this reminds you of James' rule for the decomposition numbers for the symmetric group. And actually, it is a consequence of these geometric results if you use the modular Springer correspondence. So the geometry really encodes these decomposition numbers. And so this is a general result for any 2 partitions. But if you want to look at minimal degenerations, you can say what they are. You just move one box. So either horizontally or vertically. And after removing all the common rows and columns, you get to the 2 extreme case that we already understood. So if you move horizontally, you have a simple singularity. And how much you had to go left tells you which AN singularity you have. And if you had to go down, it's a minimal singularity. And the only intersection if you just go one step down. And I said before there was order reversing evolution on partitions. And so clearly those 2 cases are exchanged by the duality. So it would be nice to have something similar for other types, but then you have to restrict to special orbits. So this is an example of type A5. So you have the poset of partitions of 6. And you can work out very easily, suppressing lines on columns, what the singularities are. And you can see the symmetry as well. So I will not go into the details of the other classical types. So you also have a row and column removal rule. But you may have to go to to switch between orthogonal and symplectic cases. And there are a bit more irreducible cases. But still, you can classify everything. So there's still results of Kraft and Procesi. And so most of the time, it's either a minimal singularity or a simple singularity. But sometimes you have two branches and you have two type A singularities. And so here you begin to have non-normal nilpotent orbit closures. But you can always detect them in codimension 2, and there are two branches. And so we had a lot of fun, and in exceptional types, you can see even many more funny things. So if I continue with this duality, so what should be the dual to the regular subregular case? So it should be the minimal special orbit, so the unique one. It is of dimension twice the Coxeter number minus 2. And so in simply laced types, the minimal orbit is already special, but in the other ones, it is not. But if you look at the minimal special orbit closure in the other types, you can get it as a quotient by the same group of symmetries of a minimal orbit closure of a simply laced type. So on one side, we have a simple singularity with an action, and on the dual side, we have a minimal singularity of ADE type, but quotiented by some action. And here you have more orbits in between. So I was not sure about the history of this, but at least for G2, I think it was observed by Levasseur and Smith, and then inspired by this, Wani, Brzezinski, and Constant did the other types. So they have a paper where they compare more pairs of nilpotent orbit closures, but in particular those. So at the beginning I said we're also interested in special pieces. So there's a Springer correspondence which associates to each irreducible representation of the Weil group a pair with an orbit and some local system on it. And Lustig introduced the notion of some special representations of the Weil group, and they always correspond to some orbit with a trivial local system, and those orbits are called special. And for those, you have an order reversing involution. And Spaltenstein had another approach where he was looking for something as close as an order reversing involution as he could get, and he found the same thing. And when you have a special orbit, you can take the closure and you remove the closure of all smaller special orbits. And then you get a partition of n. So this was proved by Spaltenstein. And they are rationally smooth. So it was a conjecture of Lustig. And it was proved case by case for exceptional types, just as a byproduct of calculating all the Stokes of intersection complexes for all nilpotent orbit closures. So yeah, just when this intersection complex is a constant. But for classical types, it was proved by Kraft and Procesi in another way. They proved that it was a quotient of a smooth variety by some finite group, which in this case was a two-elementary abelian group. And so this led Lustig to conjecture the following, so that each special piece is a quotient of a smooth variety by a very precise group. So Lustig recognized what group this should be, and it had a meaning for all types. So this gives a very nice conjecture, and it's still open. So I want to talk about the example of Juteau because Kraft had a paper about this, and before that Levasseur and Smith. But even in that case, we can say more things. So here there are just 5 orbits. They are linearly ordered. So you have the regular one, the subregular one. Actually, the minimal special is also the subregular one. And then A1 tilde is an orbit of short root vectors. A1 is a minimal orbit, the orbit of long root vectors, and then the trivial orbit. And so there are only 3 special orbits. And here you can see it's symmetric, okay? And I'm not saying much if I say that G2 is exchanged by the minimal special of G2. But still, it's D4 with S3 action and the minimal D4 divided by S3. And so the top, we know what it is, so it's D4 with S3 action. And then we have an A1 singularity, that's easy. So down we have G2, which is minimal G2, which is easy as well. And then we have a new one, which is a bit strange. So the A1 tilde orbit closure is not normal. All the other ones are normal, but this one is not. And the normalization is a homeomorphism. So it looks a bit strange, but we could get some insight about this situation. So I will denote by an interval a slice. So I take the closure of G to A1 and I intersect with a slice to A1. So it tells you how this interval looks. And we could see it is isomorphic to something, to a configuration space. So when you have any val group W, you can always do H plus H star mod W. And so these are well-known symplectic singularities. And so we could recognize this singularity here. And actually, if you really want to understand the singularity, a nice way is to embed the complex plane C2 into C7. So you have actually you can see C3 and C4 as representations of SL2. And if you had only one color, you would have as the image the minimal orbit in this representation. But the blue map would be of degree 2, and the red map would be of degree C. But if you put them together, you get a bijection, but it's not an isomorphism on its image. So actually, it's not so horrible. So if I divide the dimensions by 2, you have a well-known example. If you go from C to C2, and to T, you associate T to the square, T cube. You send a line to a cusp curve, which is not normal, and this is a normalization. So it's the same kind of thing, but okay. So this was for G2, but now we want to do all the types. So first, each minimal generation was an adventure in its own right, because we had no idea what would turn out. But finally, we find some quite general methods which work for many degenerations, and then we had to find ad hoc methods for the last one. It's not finished. So in their paper about classical groups, Kraft and Procesi said they could not extend their methods to exceptional type because they were using 2 reductions. So one was with Slaughter slices, and the other one was with classical invariant theory. So there is no such thing for exceptional groups. But actually, the slice method can be pushed a lot, and so we had a lot of degeneration this way. So here's a proposition that we can find in their article. So the problem is to compare singularities for a group G, and you have a closed reductive subgroup H, and you want to compare the G orbit and the H orbit. So if you take Z in the Lie algebra of H, and Y an element in a smaller orbit for H. You can look at the singularity of the H orbit and compare it to the singularity of the G orbit. So the first thing you want is that you have the same codimension on both sides. And then there is a second condition. You want the orbit closure GZ to have only one branch at Y. Otherwise, you might miss some other branches. But if you have those two conditions, so for example, you have only one branch if you know that this orbit closure is normal. But sometimes it's not normal, and you can still use if you know that there is only one branch, and you can read off the number of branches from table of intersection complexes. So when you have those two conditions, you can say that you have the same singularity. So we wanted to push this idea as far as we can, because we don't have the second method. So, and it worked quite well. So we need to really use the structure of the slice, but it works nicely when we just have to go into the reductive part of the centralizer. And then it gets more difficult when you have to go to the nilpotent part. But so let's say we start with E, an nilpotent element. So we embed it in an SL2 triple. So we have the Slaughter slice. And say we consider an element E0 in so I have the centralizer of the SL2 algebra, which is the intersection of the centralizer of E and F. So that's a reductive part. And so what I want to do is to compare. So I have x plus E0 in G. Now I want to compare with 0 goes to E0 in this reductive centralizer. So again, if you have these two conditions of codimension and unibranchness, then you have the same singularities. So you can apply it for E0 minimal nilpotent element. Or maybe this is, can you see despite of this? So if you have another one in between, E1, you can also compare this singularity with this singularity. So this is useful if, for example, this is a minimal degeneration, but this one has a very small reductive centralizer. You might want to get further down to some orbit, sorry, here, which has a bigger reductive centralizer, and then you might get this singularity looking from downstairs. So now we need some criterion for this dimensional coincidence to happen. So I will give some technical details, but it's just to give you the flavor. I don't expect you to understand everything in detail. But this E0 also has an SL2 triple. And so you have two SL2 triples which commute. And you can add them together to get an SL2 triple of the sum as well. And so since you have two SL2 actions which commute, you can decompose the space with weights indexed by two integers. And so here is a criterion to have the same dimension or codimension. So it's really a condition about which weights can appear. And so what is interesting for us is that if this E0 is in the minimal orbit for G, then it works. Or also if E0 is for A2, so all the eigenvalues of H0 are at most 2, and E is even, so it works as well. So maybe I want to apply this for E0 minimum. but it's minimal in the small algebra, but maybe it will not be minimal anymore in the big one. But if it is minimal in the big one, then it's okay. So we can reverse the point of view and start with E0 and look at things with commutes with it. So if you start with your Dynkin diagram, you can add the additional node of the affine type. So this represents minus the highest root. So the highest root is a long root, so it's something in the minimal orbit. So everything which is orthogonal to this will commute. So it's just the vertices which touch the additional vertex. So except in type A, you just remove one. So you have it's of oneness, except in type A. And so the nilpotent orbits have this classification by Dynkin diagram. So if the Dynkin diagram is included in this co-rank 1 sub-diagram, then we are fine. So this means that you can add this minimal orbit and you will get the same singularity. So with this method, you can get at once a lot of minimal degenerations, which are of codimension at least 4 or type A1. Because for a minimal nilpotent orbit closure, you will not get simple singularities of other types at A1. So for codimension 2, we have to find something else. So here so I said we have very different backgrounds. So you can guess this comes from Basse-Normandie. So in this minimal model program, so starting from dimension 3, you cannot expect to have a smooth minimal models. So it's a birational geometry. So you have to allow for mild singularities. So you have this notion of terminal singularities. And so there is something you can do to a variety is to take the Q factorial terminalization. Okay, so what is very nice is that it will be smooth. So the singular locus will be of codimension at least 3. So since we are working with, so now we are interested in codimension 2 things. So if we only have terminal singularities, it will become smooth. So how does it work? So Namaikawa did this for classical types and Basse-Normandie for exceptional types. So they gave the Q factorial terminalizations of all nilpotent orbit closures. So either it's just a normalization, or you can use a generalized Springer map. So you have some parabolic subgroup, a nilpotent orbit closure in the Lévy, and you add the nilpotent radical, and you take all the G conjugates. And you have a natural map which goes to your Lie algebra, and the image is a closure of a nilpotent orbit. So this is a induction procedure of Lustig and Spaltenstein. So in particular, it is an induced orbit. And so the last statement interests symplectic geometry. So two such terminalizations are connected by Mukha-Flops. Okay. But when this nilpotent orbit in the Lévy subalgebra is 0, so we get a equipoint resolution, which is a Springer resolution. So if we have a minimal degeneration of codimension 2, and we look at this surface singularity S, so the normalization is a symplectic singularity of dimension 2, and we already know it will be an ADE singularity, but we have to determine the type. And then, so if the normalization has only terminal singularities, it is smooth in codimension 3, so the normalization is smooth. So these are strange cases. And so this happens for O rigid, or for 3 orbits in A6, 2 in E7, and 2 in E8. So it's not so often. Or we have such a map, and it's in an induced orbit, and we can go to the normalizations. And so this will be a minimal model, and in codimension 2, this will be smooth. So we get a resolution with this by restricting to the normalization of the slice this Springer map. And now the point is to identify the singularity. So there is a formula by Borrow and McPherson to tell you the number of P1s in the fiber. But then you can have some monodromy. So if you look at the exceptional locus, some P1s might turn out to be in the same component of the exceptional locus of pi. And this happens when they are, so you have an action of the group of components. And so this happens when they are in the same orbit. But the number of irreducible components in the exceptional locus is also given by the formula involving Springer representations. And so in many cases, this is enough to determine the type, but only of the normalization. So if the nilpotent orbit closure is known to be normal, then the normalization is the same as the nilpotent orbit closure, so it's okay. Otherwise, we just have a result up to normalization, or maybe we have to use another method. So here are results for F4. So on the left, you have all the nilpotent orbits. So maybe it's a bit small, but so what can we see? So of course, we have a simple singularity on the top. So F4 means E6 with S2 symmetry, and the minimal singularity F4 below. And then we have other simple singularities here. So here, a D4 with S3 symmetry, other minimal ones, sometimes with symmetry. So here it's interesting, we have 4 copies of a D4 singularity which intersect at the singular point. And there are, so here's a component group of A4 of A3 is S4, and it permutes the 4 branches. So it's interesting to see a G2 minimal singularity here, and we can see also a G2 simple singularity here. And actually here we have 5 orbits which are exactly the same codimensions as in the nilpotent cone of G2 with the same minimal degenerations. And they have the same intersection cohomology Juteau. And if we compare, if we want to compare with non-trivial local systems, so here the component group is S4, and in G2A1 it's S3. But say, okay, there is a morphism from S4 to S3, and we can pull back, and then we get a perfect match as well. So we conjectured early on that we really have equivalences of singularities for the whole interval. So if we use this method of adding something in the reductive part of the centralizer, it was very well up to the subregular orbit in G2, so up to F4, A3. But then if you add the regular orbit, I think you get to F4, A2. So it's not the right codimension. But actually, we can correct this with the nilpotent part of the centralizer. And this summer, we could see that even from A2 tilde to B3, it's really like the singularity of the nilpotent cone of G2. But there was something which was very annoying, so is that for those kind of calculations, we need to find some representatives of higher orbits in the slice, but we know more or less what form they have. So we have some coefficients that we don't really care about, except from the fact which one are 0 or not. And so we needed gap to be sure in some cases. And we had a very big problem, is that we were also using some tables by Lothar and Testerman, which give information about centralizers of nilpotent elements, but they were not using the same structure constant. So it was a nightmare for a very long time. But finally, in July, we could sort this out and to see which signs we had to put or not. And so finally, we are sure of our results. Okay. So here, this is M singularity again. So this was this strange singularity with a smooth normalization. C2 normalization, actually. So it appears twice here. And so some orbits are blue, so what does it mean? They are spatial. So here is a graph for spatial orbits. And here you can really see some symmetry. So F4, F4 spatial, etc. But we have this strange thing here, 44, and here we don't know exactly how to describe it yet. Okay. So we worked out many other cases in the other types, and so that's our results for the minimal degenerations. So in codimension 2, we find simple singularities of those types. So sometimes classical, also exceptional, and this M occurs many times. And sometimes we have unions of those. So it's not, there are several bunches. And in greater codimension, so we have minimal orbit singularities, sometimes with symmetries, and then 4 exceptional ones of codimension 4, which occur only once. Well, they have random names for now. I think they will change. So I will say more about those. So this chi is a singularity in E6 between those two orbits. So this one, you can understand it. It's a quotient of C4 by mu3, the third roots of unity, with this action. So it's really different from the other ones. And then there's another one in E8 that we think we understand. So it's a twisted version, just in the same kind of twist as M of the minimal C2, so C to the 4 divided by plus or minus 1. And for the other two, we don't really know what they are. They're still difficult in E7 and E8. But it's almost all done. But of course, this should be the hardest cases. And so we can, after having done all that, we can do some observations. So yeah, I don't show you the other graphs because they are too big to show on the transparency. But I can show you after if you're interested. So what about these minimal degenerations in exceptional types? So we have this singularity M, which didn't appear in classical types, which appears a lot. Then we have this 4G2 as well, so several bunches. This C4 modulo mu3. So in classical types, it was only minimal orbit closures that could appear. So maybe the ones that remain are quotients of those, of minimal singularities. And here, so in classical types, a non-normal orbit could be detected in codimension 2 and it was not branched. So sorry, it was a branched non-normality. But here, there are cases with non-normal orbit closures which you cannot detect just by the generic singularities. So now I will come back to the spatial pieces. So there is this conjecture by Lustig that spatial pieces are quotients of a smooth variety by a precise finite group. So we have a related conjecture about what this singularity should be. So let's say you have a special orbit O and some special orbit. It always have a unique minimal orbit in the piece. So you have the special piece here. So this Lustig's conjecture is about the variety, which is a union of all those orbits. But what we are talking about is if we take a transverse slice to this orbit. So we will see all the kinds of singularities that can appear. From this point of view, we don't lose information. The only thing is, if we understand this transverse slice, then the whole special piece locally will be a product of this slice with a part of O prime which is smooth. But it's not clear exactly how to glue everything together. Should we expect to glue this into a vector bundle, an affine bundle? We are not quite sure. But maybe starting from this, it could help to solve Lustig's conjecture. So if we have a special piece and we have O, the special orbit, which is maximal, and O prime, the minimal one, and we look at this slice from O to O prime. So first, we had stated it should be isomorphic to some H plus H star mod W, where W is one of those symmetric groups up to S5. But we had overlooked a few cases, and if we wanted to work for classical types as well, here's our updated conjecture. So you can have several copies of H plus H star. So in exceptional types, up to 4. And this symmetric group can even be S2. So in that case, it's just C2n modulo plus or minus 1. But we can say in each case what are the values of k and n. So the symmetric group is related to the group of components. And so these singularities are well known for symplectic geometers, and using a Springer resolution, it's another way to find the Hilbert-Shaw resolution. And for example, the fact that we find this in the nilpotent cone, we can use the results about deformations to have a concrete deformation, because sometimes you know that there is a deformation, but it's not very concrete. So here, it is concrete. So here's a special piece of F4 or F3. So there are 3 very special nilpotent orbits. They are in exceptional type, and they are special and self-dual. So you have G2 of A1, which we have already seen, the subregular in G2. Then you have F4, A3 in F4, and E8 of A7 in E8. So, and it's the first time the component groups S3, S4, and S5 appear in this case. So it looks like the most difficult things to work out. So here are the minimal generations in the special piece of F4, A3. And so Lustig predicted many things. So he said it should be the quotient of a smooth variety by this finite group, which is a reflection group, and the orbit should correspond to the places where the points have some kind of stabilizer, some conjugacy class of parabolic subgroups of this reflection group. So for the symmetric group, you have partitions, and you have this ordering is inclusion up to conjugation of subgroups. And when I showed this to Bauer, he immediately thought about this singularity, H plus H star modulo S4, which has the same minimal degenerations. And so we conjectured that in each case, at least for these 3 very special cases, it should be like that. So it's true for G2 A1, as I said before, but this one seemed very complicated, but it was recently solved by Paul. But so he explained us the main lines, but we still have to check the details, but it seems okay. So that's very nice. And this is a missing one. So in E8, it seems much more difficult. So it's a very big special piece. And so it should be the same singularity as H plus H star modulo S5, which has this kind of orbit poset with all those M singularities. Okay. And so we can understand, so we can prove this conjecture except in those two cases, so this S5 case. And actually the second case, I think Paul had almost worked it out. So maybe the second one is almost okay, but the first one is really much more difficult. And so one consequence of Lustig's conjecture would be that at least the special pieces should be normal. And so this was pointed out by Achard and Sage. So maybe with this slice we cannot really get exactly Lustig's conjecture, but at least we can say that they are normal when this works. So except for those two, we can say yes, they are normal. So now, so I told you Bauer immediately thought about those singularities, but here's some, so because there was this precise information by Lustig, and also he had done earlier work where he found a configuration space in a classical nilpotent cone, SP6. So if you look at those nilpotent orbits, you have a poset which is like a square, like that. And so this is like the parabolic subgroups of a Weyl group of type B2. And if you do H plus H star modulo a Weyl group of type B2, you get you can write it another way. So the symmetric square of a simple singularity of type A1. And then you have this Hilbert-Shaw resolution again. And you have, so Bauer proved that a nilpotent orbit closure, if you look at symplectic resolutions, they are always of the form a Springer resolution. But there are two of them here, and it gives you the two Hilbert-Shaw resolutions when you restrict to the slice. So this was a first instance where we could see this kind of singularities. And so this is not a special piece, it's something else. So we started looking for other places which could be of this kind of singularities. So we want, so it's a quotient singularity, so we want something rationally smooth at least, so we have some data that we can check. And so here are some other conjectures about those kind of singularities for other slices. So this one is particularly big. So we have a H plus H star modulo W for type B3. So B3 contains A2 and B2. And so B2 was this case here, and we can compare to this case and it's okay. And the A2 case is compatible as well. So we have, so we can prove this. So it's a part of this this slice. So it gives some support. And so we have this other. So we have again a symmetric square of. So here we have symmetric cube and symmetric square of A1 singularity, and here a symmetric square of C2 modulo mu3, which we had seen C4 modulo mu3 before. So here we can see a mu3 again with this action. Okay, and to finish, I would like to come back to this duality thing, which is really mind-blowing. By the way, there is a work of Boyden, Liketa, Portfood, and Webster about a strange duality. And in type A, it was so they say that some symplectic varieties should be dual in some way, and it's related to causal duality. So for nilpotent orbit closures in type A, it was clear what they had to do, but for other types, you have this special orbit business. So there should be also dual singularities between special orbits. But there is only, sometimes it gets weird, it doesn't quite work. So you have this canonical quotient of Lustig, and it has a kernel sometimes, and you want that it acts trivially on the singularity. If not, then we don't know. It's weird. But otherwise, you look at some minimal degeneration between special orbits and their duals. Then one of them is of codimension 2, and the other one will be a minimal special. So it's of dimension twice the Coxeter number minus 2 for some subgroup. And George Lustig told me that he had observed this duality for the dimensions. But it's really a duality between singularities, it seems. But we have absolutely no explanation for this. So thank you very much.
Thank the speaker again.